Okay, so in this PowerPoint slides 2, we're going to talk about problem-solving fundamentals. And in this slide presentation, we'll have kind of three main parts to it. First, the problem-solving fundamentals. We'll talk about the problem-solving cycle, which we've talked about in class briefly. Also do some additional thoughts, and I'll give you a problem example from my own life. So we'll dive in here. Just briefly, Merriam-Webster defines a problem as a question raised for inquiry, maybe a mathematical or physics problem, or maybe just generally an intricate or unsettled question, or something that's perplexed you or distresses you or vexes you. And that's kind of a old English word for just means makes you irritated or unsure or kind of a negative connotation in not knowing something. But basically, we come to problems in all parts of our lives, both in our personal lives and in school and in definitely professional technical scenarios. If we look at some common problems in industry and agriculture, there's tons of problems related to quality that we have an opportunity to solve. There's a lot of technical problems, right? A lot of the work that technologists do is solving technical problems as well as quality problems. There's a lot of economics problems, right? This is where we kind of move into more of the engineering management, business management, technology management part of problem solving. There's also public relations problems, right? Which some of us may not get as intricately involved in, but just to show you that there's lots of different categories of problems that we're going to experience when we get out into the industry, whether it's in the industrial manufacturing environment or agricultural environment. And all problems have cause, right? Or causes. And probably the thing that we're most used to experiencing is the symptom. The thing that is what we feel, taste, smell, see, right? We eat a bag of potato chips and we find metal shavings in them. Okay, this is an actual real example that I had the opportunity to work on a project in my previous employment where a manufacturing company of potato chips had problems with metal shavings getting in their bags of potato chips. And so that was a real option that somebody could open a bag up and be munching on Lay's and all of a sudden there's a metal shard in their teeth or in their gum, right? But that was the symptom, right? What was the deeper cause? What was the root cause? Well, the root cause is what's below the surface. This is what really is at the root, surprise, surprise, of what the problem is and what's causing the problem. And of course, in the example I gave of the potato chips, there was somewhere on the machinery that metal was being worn away and the filings were getting into the potato chips as they were being manufactured and packaged. So one thing when we think about solving problems, we really do want to focus on the root causes, okay? The things below the surface that are causing the problem, and not really worry about the symptoms, okay? Those are things we just feel, see, smell, taste, right? We could put a Band-Aid on it, right? But that's really not going to take care of the deeper problem, which is we got to get an antibiotic to fight the infection. So, two options to that previously stated problem, right? Metal detector at the end of the production line, just to tell us when there was a bag with metal in it, or modifying or redesigning the actual machinery to eliminate the metal wear falling into the bags of chips. So two different options. If you think to remember, ask me which option ended up being the solution to that project that I had experience with. It's an interesting solution that we used. So now turning to the fundamental problem solving cycle, right? We've talked about this briefly in class. It's systematic and it's cyclical, meaning repetitive. Also, you're going to use some variation of this process in all different scenarios, both in your undergraduate, graduate, or professional lives. So what we present in this course is a template or a fundamental version of it. There's lots of different versions, but this is just a version I feel is very applicable to what we're going to be doing. So we've looked at this already. We have 6 phases: define, identify, determine, produce, analyze, and communicate. And of course, being cyclical, being in a cycle, right, a circle. So if we look at the define phase of problem solving, we need to come to a good problem question, okay? That's what I'd like us to get practice doing, is taking a problem and boiling it down to a simple, straightforward question, right? And a lot of times we really need to think about what are the properties of the problem, what data are we talking about. We'll get to the data in a little bit, right? But really the two things that really stick out are, what do we know about the problem and what don't we know about the problem? Because 9 times out of 10, we're going to try and find out what we don't know about the problem, and that relates to our solution. Okay, of course we need to know what's important or relevant, okay, and also what's irrelevant, not important, okay. But really, kind of taking these two here, given or known and unknown, okay, and that really can help us boil down our problem into a question. And of course, this phase drives all the other phases. Step 1 affects all the rest of the steps. So let's not take this step very lightly. We also need to identify assumptions, constraints, and criteria, and we'll look at assumptions first. They're basically just theories, laws, influences, or ideas that we're either going to accept to be true or basically say we're not considering those to affect our solution. So an example might be things that you don't want to affect your solution, like you're trying to figure out grain prices in Iowa. Well, you don't care about grain prices in Illinois or Minnesota, right? You're assuming that you're only talking about Iowa. Or things that help define the scope of your solution, right? An assumption being we're going to be looking at a forming process in a manufacturing plant, and we're going to be looking at the forming process of car hoods, so the metal hood of a car, right? The forming press, right? We're only going to be talking about Toyota Camry car hoods forming process. We're not going to talk about Chevy pickup trucks or Mitsubishi whatever, right? So assumptions kind of help us carve out the scope and also help us identify things that we either take for granted or things that won't affect our solution. This helps frame what we're trying to do. And of course, constraints and criteria are very important. Constraints, those physical or practical limitations on problem solutions, the rules you have to live by. You cannot violate a constraint and have an appropriate, effective solution. Okay. Criteria then are the desirable characteristics of a solution, things a good solution has, right? It's cheap, it's high quality, it's really fast. You can manufacture it fast, right? So this brings me to an example that when things are manufactured, they usually exhibit these 3 criteria: cheap, fast, or good. Okay, and you can only get 2 of these 3. Okay, so you can either have something that is very cheap and very good quality, but it takes a long time to manufacture. You may have something that's cheap and really fast to manufacture, but the quality is pretty low, pretty shoddy quality. Or you have a very good, very fast product, but it is doggone expensive, right? And of course, to get all 3, cheap, fast, and good, it's not going to happen, right? When we manufacture something, we're always constrained by these criteria, and we can't make all the criteria maximized. Basically, we can't get a free lunch, right? We can only get some of them maxed and other ones not quite maxed. So we're always balancing criteria when we solve problems, right? How do we get as many of them maximized as possible? And usually when we can find that point, that solution is probably our best solution, as long as we're not violating any of the rules, the constraints. Turning to appropriate data. Now this is really the meat of what we use to make our analysis, right? We build our analysis on data. What data do you need to answer your question? That is probably the key here. Answer your question, right? The data always has to point back to the question that we're asking. And so an example here, how can we increase efficiency? So we're trying to increase efficiency, less waste, more output of a grain loading process. So examples of good appropriate data could be causes of waste grain, right? tasks that require to operate the loading process, right? What are the different tasks? And then hourly rates for the people or the operators doing these tasks. So where's the grain being wasted? What process or tasks are being done? And how much money is being spent per personnel? And you could even extend that to how much grain is being wasted and how much does that cost, right? Maybe some poor and inappropriate data could be the different grain types. Maybe that affects it, but not really directly. Number of trucks, yes, but you're always going to have this percentage of waste no matter how many trucks you have. Safety hazards, they're important, but they don't get at this question, right? Remember, we're always trying to get back to this question, okay, and increase efficiency. These are appropriate data for different problem questions. For this one, not so much. So we just got to remember, when we look at data, we have to always be tying it back to our question. Another one being making a metal forming process more safe. And of course, existing design, existing safety hazards, how many different types of hazards, pinch, crush, those types of things. Alternative designs, possibly, all good data to help us get to a safer product. Things that maybe are not appropriate, how much we're making per hour, what we want to make in the future, how much it costs to operate the process. These are good examples of data, but not very good examples that relate to making something safer, okay? So we always remember, if we're asking a question, we need the data that can help us answer that question. And of course, we need to go collect the data, okay? We need to be realistic about this. We can't collect all of it, okay? And we're probably always going to have a subset of the data, okay? We're not going to have all 100% of the data we could collect. We're going to have 90, 80, 50, 10% of the data maybe. This is where statistics helps us, okay? Talk about that in the future here. Also, we can't spend indefinite amounts of time and money, right? We're constrained by time and money usually. Now, big data things like applications that track everybody's data all the time, every hour of the day, right? Those are allowing us to get closer to 100% of data collection, but we're never going to get 100% data collection. Or the flip side of producing data is the alternatives. In a situation where we want to design or redesign a product, a lot of times we come up with multiple design options, okay? And usually keep this to short list, about 3, and really making sure that you're doing your due diligence to make sure that these designs are concise, valid, thorough, right, within the constraints, right, that they're good design options, and that you're not forgetting the problem criteria. But basically, we lay out 3 different design options, and then we would rate them against each other to see which is the best design per the criteria without violating constraints. Okay, so kind of 2 different ways of approaching either more traditional collect data, analyze the data with like statistics, means, and proportions on the top here versus the bottom being redesigning a product where you come up with different alternative designs and you decide which one is going to meet the question that you're asking the best, right? And of course, best being something we define by our criteria. We're going to analyze the data, okay? We're going to do this in a number of different ways. The big thing we got to be careful of, we do not want to violate constraints. We want to meet our criteria, okay? We want to make sure our solution is based on the data, okay? We want to use common sense, and we always want to step back and say, does this solution to this analysis seem appropriate, and does it really answer the question we're asking? Okay, and we're going to do some mathematical stuff. We're going to do some statistics stuff in this class that we're going to get at how we analyze our data in different ways. Just a real quick design matrix example. This is a really, really helpful tool when you have alternative designs. And basically the way these work, a lot of you will be using these, is you have your different design options here on the left, and I have different antenna designs, and I looked at some different journal articles. This is a past project I did. Looked at some journal articles with some different antennas that these individuals had, and I looked at the criteria, 3 criteria: gain, right? How strong of a signal that those antennas could receive, the frequency band, that they could receive in, and how quickly or available I could get them. Okay, and for each of these criteria, based on each of these alternatives, I rated them between 0 and 3. Okay, and I came up with this ranking. I came up with the ranking, okay, based on gain, different values, frequency, different values, availability, different values. It's a 1 if it's custom, right? It takes a long time because I have to manufacture it custom. It's 2 if it's off the shelf. I get it real quick. I can get it off of Amazon in 2 days, right? And so the general idea here is that you're rating each individual option per each individual criteria, and a lot of times you go with a highest score wins, right? And so you add up all the ones across the criteria, and the one with the highest score is theoretically your best design, right? Because it has scored the best on each different criteria. So this is the maximum points you can get in this criteria for all these criteria. So you've maximized your criteria with the second option there. Okay, the other ones aren't a maximized solution, right? They didn't score as well on the criteria. So this is just an easy way of analyzing between different alternative design options. Finally, communication. The end of the phase, right? The last phase, one of the most important phases. You can have a great solution, you can have a great idea, you can have a great design, but if you do not communicate it appropriately or clearly, nobody cares, right? And really, this is, from what I've found to be true, perception is everything. People will, what they perceive you are saying is the reality of what you're saying to them, okay? It's even more important than the facts, right? What they hear you saying is more important than the facts, okay? So we really have to be clear. We have to know our audience, okay? We have to know who we're talking to, okay? If we're talking to different people, we need to communicate differently, right? Whether I'm talking to somebody in a manufacturing scenario versus somebody in an agriculture scenario versus somebody in Kentucky versus somebody in Australia, all these different audiences that we're going to communicate to, we have to take that in consideration. But above all, really boils down to logical, organized, impactful, and concise. Okay, we're going to hopefully by the end of the semester, we're going to be able to get our solutions into a logical, organized, impactful, and concise form to communicate them. Okay. Now, one strategy we can use to help us communicate clearly and effectively, and oftentimes in a very short amount of time, is the STAR approach. This is commonly used in interview scenarios where you need to quickly and concisely communicate a past experience that you had and what the outcome was, usually hopefully positive. But we can also use this when we communicate our solutions to problems we have solved, or even what we've done to date on a problem or a project. And so it has 4 parts, S being the situation in which our problem solving took place. This helps the audience understand the setting and really kind of orient them to what we're about to talk about. Then there's the task. What was it that we were trying to accomplish? And this really gets at what our goal is or was in the problem solving. Then the action. What did we do to solve the problem? Or what were the things that we tried to do to solve the problem? And then key, the result. What was the outcome, or how well did we solve our problem? And so one example from my past experience when I could use this to show you kind of how this would work would be starting with a situation. I had an opportunity to work at the Harley-Davidson Softail plant in York, Pennsylvania, and for a 2-week period. And what I was tasked with doing was, on a technical standpoint, babysitting an RFID tag line. But really the primary task I was doing was there was a coworker that had been working there for months on end, and he was at a point where his wife was going to leave him if he kept on working there for another weekend. And so I was asked to go sit there at the plant, watch the line, make sure nothing broke for 2 weeks so that the coworker could stay home and kind of mend his marriage. And so what I did at the plant, my action was, I went there for 2 weeks. I sat there, watched the plant line where they would paint all the frames, and we would track them with RFID tags just to make sure nothing would break or nothing stopped working. And I did that for 2 weeks, and the result was, to my best of my knowledge, the coworker is still married, happily, and the line at Harley Davidson never went down. And so that's just an example of how very quickly, in about a minute or so, I was able to express a situation, a task, an action, and a result that I had from a previous experience to communicate to you how I solved the problem, what the result was. So we can use this approach, this STAR approach, when we communicate the solutions to our problems in this class and outside of this class. And really what it does is it gives us kind of 4 really easy categories of how we want to phrase our response or our communication. It breaks it down into kind of 4 parts and really getting at clear, concise, and quick communication. So, just as a wrap up for this fundamental problem solving, we have these 6 cycles, but we always need to stop and think. We always need to step back and think about what we're doing, and it should always be, all these should be pointing back to our question, right? We should always be going back to what is the question that we're trying to ask and solve. Okay, if we're not doing that, then we need to stop and refocus on what our problem question is. Okay, so now there's going to be some additional thoughts, just some quick additional things, and I'll finish up with the example. So additional thoughts being, there's lots of ways to solve problems, especially in quality environments and industry. And so a lot of you will go into a scenario where you need to make something better, cheaper, faster. You need to get rid of defects or waste, right? And you're going to take TSM 310 possibly if you continue in this major, and that's going to really talk a lot about these quality problem-solving tools. But definitely ones we're going to talk about in this class are Pareto charts, scatter plots, and histograms. Just a Pareto chart is something that looks like this. We'll talk about it in more detail when we get to it, but you basically are able to identify the few things that account for the majority of the overall cost or defects or whatever you're looking at. And so this is where the Pareto principle comes into effect, where it says that 20% of your items account for roughly 80% of your costs or defects or time or what have you. Okay, and that's been found to be a pretty common rule of thumb across all different industries. Other scatter plots where we actually look at plotting our data on an X versus a Y axis, and then we can do a trend line, and so we can actually generate a mathematical equation that kind of describes on average what our values will be. And a histogram or a frequency distribution, it's how many times do we get a value in the 445 range? How many times do we get a value in the 475 range, right? And this helps us almost like test scores, right? Bell curve. This helps us see how the data is distributed, where the most commonly occurring range of data is in the 455 range, right? So we're going to talk about those also. Just a little preview. But there's lots of different tools. We're going to focus on Excel. We're going to focus on programming, okay, towards the end of the semester, and we're also going to focus on math and statistical models to help us analyze. Okay, but really we got to think about using the right tools for the right situations. And then finally, I'm just going to run through a quick example here of a problem that I had, or a problem that I was trying to solve, get an answer to, right, from my own life. And I'm going to run through all the different phases and kind of show you how I would run through this with an example of what I've just described. So my problem, the way I would define the problem I'm trying to answer is, am I an expert at anything? Sit here, I've worked for 10 or so years, I've been in grad school for another almost 5 years, right? Am I an expert at anything at this point in my life? It'd be nice to at least be an expert in something. And the things that I know, I have a lot of experience in electrical and electronic systems. I have a lot of experience in robotic systems, as well as project management. The thing I don't really know, or it's really the crux of my question here is, do I qualify as an expert in any of these areas? And of course, the assumption that I'm making is that 1,000 hours of effort towards something means I'm an expert at it. So if I spend 1,000 hours doing one thing in my lifetime, I could be considered an expert at it. People have said that that's kind of the amount of time you need to spend on something to be considered an expert. So I'm going to use this assumption, right? I'm going to constrain myself to only professional hours, basically hours I've worked at a job related to these three categories of electrical electronic systems, robotic systems, and project management. And of course, I want to say the quantity of hours, right? The more hours, the better. And the data I'm going to use is hours per category. How many hours have I spent all the way up till today on these different categories? So that's my determine appropriate data. And to produce data, I'm going to do some calculations, and really what I'm going to look at is trying to understand how many hours per category I've worked. And I'm going to look at how many hours per category, how many years I've worked in each category, how many hours a day I've worked on average in those categories, and how many days a year that is, right? So I can calculate total hours per category, right? I'm just going to run this simple multiplication for each of the different categories. Doing that, I see that I have 10 years I've worked in each of these categories. I've worked roughly 4 hours, 2 hours, and 2.5 hours per day in each of these. And I've spent 260 days a year, so that's 52 weeks times 5 days a week. So that's like a very common number of days a year that you'll work. And then of course then 10 times 4 times 260 is 10,400, right? And so it looks like from basically, you can see this from the table, but you can also see this from the graph here, that electrical electronic systems I have the most experience in, and it's above that 10,000 hour limit or line. So based on this data analysis, I would conclude, right, and also definitely based on the constraint of only using professional time and the assumption that 1,000 or 10,000 hours means I'm an expert, I could be considered an expert in electrical systems related topics or projects. So that's just a quick example of how I would run through. I've hit all 6 phases. It's important in the communication to link back to your constraints and your assumptions and criteria, and then to clearly define at the end, like, to answer your question, right? So I hope this has been helpful. I hope that some of this stuff is starting to become clear. We're going to work more with these things in class, and I hope to see you shortly in class. Just some final thoughts. Be patient, right? A lot of problems, it takes time, and it takes stepping back and looking at it from a different perspective. Try to simplify whenever possible. Cut it into small sections, okay? The Romans conquered the world by dividing things into small areas and conquering each of those individual areas one at a time. Good luck.